Okay, so today I'm going to talk about the importance of long-range electron interactions on the magnetic phase diagram of twisted bilayer graphene. This work was done in collaboration with Leonard and supervised by Dante, Arish, and Johannes. So as we've had some really nice reviews of twisted bilayer Moiré materials today so far, I'm going to keep this quite brief. So what happens when you twist a graphene sheet relative to another one to create a twisted bilayer graphene is you shift the graphene, or the direct tone of one of the graphene layers with respect to the other one in momentum space. And because these graphene layers can hybridize with each other, when the momentum misalignment between these two direct cones matches the hybridization energy between the layers, you can get the emergence of extremely flat electronic states at the Fermi energy. And when that happens, the electron interaction energy becomes the dominant energy scale of the system. And as we know, we get the emergence of broken symmetry phases. So in twisted bilayer graphene, well, I go correlated insulating states and superconductivity were reported. But since then, many of the interesting properties have also been reported, such as pneumatic order, the Dirac revivals, but I'm not really going to go into that direction here. What I want to focus on in this talk is the qualitative behavior of magnetic phases as a function of doping, and in particular twist angle around the first magic angle. So in experiments until quite recently, actually, people were quite focused on constructing devices that have highly uniform twist angles over the whole device. There's very little strain or twist angle variation. But this doesn't really lend itself to understanding in detail the variations of these phases as a function of twist angle around these phases, around the magic angle, because you have to construct lots of different devices and there can be variability between these. So we wanted to make some predictions of what kind of happens as a function of twist angle. Right, and so to do this initially, we used an atomistic Hartree type binding theory, just to look at the normal state of twisted bilayer graphene. So what we do in this theory is we construct and diagonalize our Hamiltonian and generate the electron density from the occupied states of these eigenstates. And then using the electron density and a screened interaction, we determine the Hartree potential, which is then included as an on-site energy in the Hamiltonian, and we need to self-consistently solve for the electron density, basically. So this is quite expensive to do actually at the magic angle in a tight binding model, because we have about 12,000 electrons in our PZ orbitals. But this is significantly cheaper than, say, doing a DFT calculation, which is basically impossible to do a kind of fine twist angle and doping dependent study at the magic angle. Right, so here is the electronic structure of twisted bilayer graphene under two different approximations. In the upper panels, I'm showing the tight binding approximation. So there's no electron interactions here. And you can see that the electronic structure doesn't have any doping dependence other than where the Fermi energy sits within these bands, as you can see. Whereas the Hartree electronic structure acquires this sensitive dependence to the filling level of the electronic structure. So you can see that when we add electrons into the system, the states are M, K shift up in energy relative to the states at gamma. And when we remove electrons, the states at M and K shift down in energy relative to the states at gamma. So at a twist angle of 1.4, actually these Hartree interactions are not the dominant energy scale, and the band deformations that occurs from these interactions is quite modest. But as we go to an angle closer to the magic angle, such as 1.2 degrees, we can see that these Hartree interactions are really becoming quite dominant. And in fact, when we reach +3 or -3 electrons for the doping level, we can see that we have this really quite interaction-induced band flattening occurring here. So even further, right at the magic angle of 1.05 degrees, we can see that adding and removing electrons from these flat bands causes quite extreme band deformations. And this is because the Hartree energy, this is basically the dominant energy scale of the system at this twist angle. And the electronic structure is qualitatively different when you add electrons to when you remove them. You can see different shapes. Right, so these Hartree interactions appear to be quite important, and you can see that they're inducing flat bands at kind of twist angles, doping levels where we wouldn't expect flat bands to occur just based on the twist angle. And this could have important consequences for, say, the magnetic ordering of the system. So to put this on more of a quantitative footing, what we did was calculate the non-interacting spin susceptibility using the single particle Green's function. And using that, we then calculated the full interacting susceptibility. And what this tells us is that when this susceptibility diverges, we would expect the onset of a magnetic phase. And two pieces of information that we can get from this is the critical on-site Hubbard parameter of the PZ orbitals required for the onset of a magnetic phase. And it can also tell us what type of magnetic phase is occurring. Right, so now we can look at the results for this, and the top left-hand side are two panels. What I'm showing you is the critical on-site Hubbard parameter required for the onset of a magnetic phase as a function of doping and twist angle for two different approximations. So the tight binding, where we don't have any electron interactions, and the Hartree case, where we are including these interactions. And so what we see that in the tight binding case, we predominantly expect magnetic phases to occur right around the magic angle, mainly for whole dope systems. Whereas with these Hartree interactions, we expect something that is, well, really quite different. And so we can look at the magnetic phases of each of these different doping levels and twist angles. And there was something that I forgot to say. So in graphene, the Hubbard interaction of these PZ orbitals is about 4 electron volts. So what we've done in these two diagrams is either colored in regions where we expect magnetic phase to occur, so in red, and where we don't expect it to occur in gray. So that's when the critical Hubbard interaction strength is larger than 4 eV. And what we've done in these lower panels is we've just hashed them out where we don't expect these magnetic phases to occur. So the red phase is a modulated antiferromagnetic phase, which is peaked in the AA regions of the Moiré unit cell. Orange phases are a nodal antiferromagnetic structure, which are again peaked in the AA regions of the Moiré unit cell. And our blue phases are ferromagnetic order. And ferromagnetic order appears to occur where basically the bands are the flattest. So in the tight binding case, this is for electron whole dope systems right around the magic angle, as you can see here. When we include these Hartree interactions, we actually find something quite different. So now we find ferromagnetic phases, twist angles away from the magic angle, and they usually occur more towards plus or minus kind of 2 and 3 electrons rather than sort of -1. So what we can do is we can look in a little more detail into what we expect from these two different approximations and compare against experiments. So here I'm just going to focus on one of the doping levels. So we're going to focus on the +2 doping level. And in our tight binding case, we wouldn't expect magnetic phases to occur, as we can see here. But in experiments, actually the ±2 insulating states, some of the most robust, and they were the first ones that were reported. So that's clearly quite some bad agreement between the tight binding approximation and experiment. But if we then include our Hartree interactions, what we find is that we do expect some magnetic phases to occur. And this is in better agreement with experiments. And actually, we can do this for pretty much all of the doping levels and find generally the heart tree calculations agree better with experiments in the tight binding case. And for a few a full discussion of that, you can see our paper in PRB. So I'm going to take a bit of a step back and more generally now look at the qualitative behavior of the magnetic phases as a function of doping level and twist angle in these two different approximations. So for the tight binding case, as I've said, right at the magic angle, we expect magnetic phases for pretty much all of the doping levels. And as we move away from that magic angle, we expect the prevalence of these magnetic phases to diminish. And this is more pronounced as you go to doping levels further from charge neutrality. So you can see +3, we don't really expect anything away from the magic angle. Whereas when you include these heart tree interactions, we basically expect the opposite effect. So as you move away in twist angle from the magic angle and to larger doping levels away from charge neutrality, we basically expect more magnetic phases to occur in the system. And so interestingly, in some recent experiments by Youngjo and Choi, which we'll speak in the next session about this, this is actually really similar to what has been recently observed. So this is I'll just show you some quick results of this. So basically what they observe in their STM experiments is that at, say, a larger twist angle of 1.15 at +3, they start to see signatures of correlated phases. And as we reduce the twist angle towards the magic angle, insulating states
3 minutes
start to occur at doping levels closer to charge neutrality. And yeah, I guess we'll find out more about this in the next talk. So in summary, heart tree theory causes large deformations to the electronic structure, as first predicted by Guinea and Villat. These heart tree interactions induce band flattening in addition to the twist angle band flattening that occurs, which induces more broken symmetry phases. So it seems to be quite essential to include these interactions when predicting the twist angle and doping dependence of magnetic order in twisted bilayer graphene. And these heart tree interactions could have some important consequences for superconductivity too, for mechanisms which require a high density of states, such as spin fluctuation or electron phonon. But what about other graphene-based Moiré materials? As we know, there are quite a few other ones now. So one of the systems that is generating a lot of attention now is the twisted tri-layer graphene that Alan McDonald nicely introduced at the start of today. So we won't repeat that here as much. But basically for the heart tree theory calculations of the system, what we find is something analogous to twisted bilayer graphene. So the electronic structure acquires this sensitive doping dependence again, and we get these strong band deformations. So I'd like to point everyone to a poster by Eamon Fisher on Wednesday. He's going to present some results on superconductivity in the system based off spin fluctuations, and also our archive preprint on this topic. Okay, so whereas materials such as twisted double bilayer graphene, which also have quite similar electronic structure, apart from the gap at the K point, what we find is that in this material, actually the heart tree interactions are extremely weak and don't cause any band deformations to occur. And similarly, a new material that we've started to look at is mono trilayer graphene. So this is quite similar to the mono bilayer system, where we're using an ABC stack of trilayer. And again, because of the aligned layers, it kind of appears that the heart tree interactions are not really strong in this system. And I'd like to point everyone to a talk by Leonard later in the week on Thursday. He's going to kind of discuss the magnetic phases in the system.